Welcome to section 10.2, where we focus on hypothesis tests about proportions. And then in 10.3, we'll focus on testing the mean. And here's a list of ways we think about that. An event with probability less than 0.05 is considered unusual. That's been a theme so far. Would you expect that particular thing to be unusual? And if it happens in less than 5% of the time, we consider that unusual. That corresponds to tossing heads maybe 5 times in a row, something like that. That's unusual. If an unusual event happens, we call the result statistically significant. Right, so if something unusual happens, we are drawn to try to figure out why that unusual thing happened. Statistical significance causes us to doubt the validity of how we computed the probability of the event. Sure. So if something happens and it's not supposed to happen, well, maybe the reason we think it's not supposed to happen is because we're basing that thinking on something that's not valid. I get that. In hypothesis testing, the null hypothesis describes how we compute probabilities because it tells you what values we're going to stick into the test statistic. Those values could be correct or incorrect. And so seeing an unusual value would cause us to doubt the values we plugged in that came from the null hypothesis into the test statistic. Okay. A statistically significant result, what does that mean? An unusual result based on what we used for the parameters. A statistically significant result favoring the alternative causes us to reject the null hypothesis. That's how we decide. Something unusual happens based on using the values in the null hypothesis. We say those values might not be right. We're going to reject them. Statistical significance can be stated in terms of the test statistic or some test statistic or the p-value. Those are called the classical and p-value approaches. So over here, we have an example of at least the classical approach applied to coin tossing. You wonder if a coin is being tossed fairly. You will observe 2,000 tosses. The classical approach, it looks like this. You set p hat equal the number of heads over 2,000. Then if p, the actual proportion, is a half, p hat has a nearly normal distribution with a mean of a half and standard deviation of 0.00188. And so we could compute z that looks like p hat minus 0.5 over 0.01118, like that. And then we're looking at, is z bigger than 1.96 or is z less than minus 1.96? Those would be the unusual values. And we could find those places out by, we said that's the 95% probability they'd be between here and here. So 5% of the time, the answer would be yes to those, and those would be the unusual values. You find those places by taking 1.96 times the standard deviation and go that far away from 0.5, and that gives you a p hat or a p hat, those values. These p hat makes this happen. So we can either use the z value or the actual p hat value. So more than 52.19% heads and less than 47.81% tail heads. When we make us think the coin is unfairly tossed, because it's pretty hard to get that fraction by accident. In number of heads, this is more than 1,044 or less than 956. So more than 44 away from the center, which is 1,000. 1,000 plus 44 or 1,000 minus 44 is far enough away that means the coin isn't being tossed where there's a 50-50 chance of having heads. You wouldn't see those kinds of values very often at all if it was 50-50. So that would be the classical approach, seeing a number of heads in this bigger than this range, seeing a p hat in this range, or seeing a 1.96 in that range. Any of those statistical values, the test statistic, the actual p hat statistic, or the number of heads statistic, they all amount to the same strategy of finding how big something has to be considered unusual, how small it has to be considered unusual, and looking for stuff in that range so you can reject the null hypothesis. So we say here we reject if z is bigger than 1.96 or less than minus 1.96. We reject if p has bigger than 0.5219 or less than 0.4781. Or reject if the number of heads is bigger than 1044 or less than 956. Those are all the same strategies in this situation. But each of them you have to kind of understand what's happening here. So we would have to know, how did you do all this? I don't understand something you might say, because I don't understand coin tossing. All I see is stuff. Like, I don't know. I mean, if I didn't know what coin tossing was, I might not know what 1044 or 956 heads really meant. I might not know what p hat's supposed to be for coins. I probably know z is not supposed to be this big if this thing's being computed correctly. But if we drop all this and we go to the p-value approach, then we just look at the p-value and see how tiny it is and make a determination that way. So there's 2 ways to go. There's actually 4 ways, because I have 1, 2, 3 classical ways, and then we'll go ahead and look at the p-value. So for the p-value, I don't have to mention any of this directly. I'll just say if the p-value is less than 0.05, I'm going to reject the null hypothesis. It incorporates all of this information in one way or another into a unified framework. And that's why we accept it as the gold standard of how you're supposed to report hypothesis testing, because you can compare that p-value across a family of statistical procedures without understanding the nuts and bolts of the procedure itself, which sometimes are very complicated. You just see the p-value, and the p-value is small enough, you go, well, we're going to reject the null hypothesis. That's all there is to that. And so we'll spend some time next on moving this over to look like the p-value approach, and then see where we go from there.